thrust assessment is the weight and balance of the Albatross. This ball represents the centre of gravity, or the CG. This blue bar represents the mean aerodynamic chord, the front of which has a z coordinate of 0. For the CG, the 0 in the z-axis indicates the CG is at the leading edge. This arrow is along the z-axis, which shows it's the longitudinal axis of the Albatross. Moving this forward causes the z-coordinate to become more negative, and moving it backwards causes the z-axis coordinate to become more positive. I have now loaded the weight and balance experiment from the Flight Dynamics Lab Manager. We can see that the Albatross and each landing gear resting on weighing scales, showing the mass reaction on each scale. Since we know the positions of the landing gear relative to the Albatross, if we know the forces on them, we can calculate the moment arm on them, and hence calculate the measured centre of gravity values, which are different to the initial test CG values. As you can see, changing the longitudinal position of the CG alters the mass balance on each landing gear. The location of the test CG can be incrementally varied. The total load can be calculated. Multiplying the measured load and the moment arm gives the moment. The total moment and measured load interact to find the measured CG value. The measured CG values can then be plotted against the initial CG test values. Theoretically, a y is equal to x sort of trend passing through the origin would be desired, but this small discrepancy from the origin is not too significant. Another important implication to know in design is the nose and tail tipping moments, as this puts a limit on your longitudinal CG position. The tail tipping point occurred when the longitudinal CG exceeded 0.15, and the nose tipping moment occurred when it exceeded negative 0.34. As you can see, if I exceed the longitudinal position from 0.15 to 0.16, the Albatross will tail dive backwards. In the same way, a CG Z coordinate of negative 0.35 would cause a nose down tipping moment. Next, we brief on the thrust test experiment. Near the nose of the Albatross is a force sensor which will indicate the thrust level produced relative to the level of RPM that you input. The static thrust can be found when the CG is at 0.05. The RPM can be seen on this dial amongst many other flight displays over here. The RPM can be increased to 100%. The measured thrust relative to the full RPM is 28 newtons. Recording such data for multiple RPMs allows us to plot the static thrust per RPM. This gives the controller an idea of the static thrust, which varies at different points from this calibration.
In the static control response, some control surfaces needed to be reversed. After correctly configuring the input matrix, as shown here, the correct control surface movements are as follows: flaps down, roll left, roll right, yaw left, yaw right, pitch up, and pitch down.
In the dynamic control response, page up and page down are responsible for controlling trim induced by the elevator on the keyboard. Having increased the wind speed to a more realistic value, the trim can be seen here, and the sign of the change in trim angle is consistent with the elevator input. The pitch response is also consistent with lift and the tailplane. For CG and wind speed, short period response can be observed when the elevator is engaged.
The short period response can be observed for the CG position and wind speed by engaging the elevator. The data for this is extracted into Excel. The Albatross was tested for pitch response across 3 different CG locations, 0%, 25% and 50% of the mean aerodynamic chord at 4 different wind speeds to replicate free stream velocity. This was at a max velocity of 27.7 meters per second, a stall velocity of 10.5 meters per second, and 2 velocities in between. The graph showed that as the airspeed increases, the elevator response is more rapid. The short period response reduces in magnitude with a higher damping ratio and frequency. As the mean aerodynamic chord percentage increases, the short period response becomes larger. At 0% mean aerodynamic chord, the elevator input varies by only about 5 degrees. For 25% of the mean aerodynamic chord, this is almost 18 degrees, and over 30 degrees for 50% of the mean aerodynamic chord at stall speed. The short period frequency at cruise is also plotted. The short period is found to be 12.7 radians per second, which is slightly lower than the Albatross datasheet value of 13.357. This isn't too significant. Finally, the most aft position at which acceptable pitch control can be maintained is at 25% of the mean aerodynamic chord.
For lateral dynamic response, different levels of aileron inputs can vary the roll rate. The data logger shows the difference in a faster and a slower roll rate.
Once again, in Excel, we can observe how the free stream speed affects the roll rate of the Albatross due to aileron input. As expected, with a greater free stream speed, there is a quicker roll rate. Looking at the yaw input during cruise, the damping of the yaw response is lower than the damping of the roll. The dynamic control response, the thrust line of the Albatross is offset. This causes thrust-pitch coupling. The CG location was altered along the vertical axis and the angle of attack change yielded for each experiment was recorded. This was plotted. This plot identifies the location where there is zero thrust-pitch coupling. The zero coupling CG position was found to be at negative 0.03821. Next, we conducted wind tunnel testing. This was tested for a set number of alphas, whilst parameters such as CG, position, flap setting, and elevator deflection were all set. This was run, and the data for these static wind tunnel tests were recorded in Excel. If we look at the plot for the lift coefficient against the angle of attack for three different flap settings of 0, 20, and 40 degrees, the max lift coefficient for each flap setting is noted. You will notice an increase in the max CL as the flap setting increases. Each of these max CLs occurred at 10 degrees. According to the Albatross datasheet, the max CL is assumed at 1.4 for flaps deployed and 1.2 for zero flap input, and the max CL occurs at an angle of attack of 12.834 degrees. This is the lift coefficient versus drag coefficient graph for flap settings at 0, 20, and 40 degrees again. You can also see the behavior of the CLCD during stall in this plot after the max CL points. You can have negative CL, but not negative CD because drag always acts in the opposite direction to the Albatross's motion. Furthermore, the CL can be plotted against lift and drag ratio for the same flap settings as before. The maximum points on each line show the max lift to drag ratio for that flap input. These are shown here. As expected, with a greater flap input, the lift force increases. The CL at which the max CL-CD ratio occurs is also noted. According to the datasheet, the cruise CL-CD is 30, as calculated here. The CL-CD measured is quite a bit away from this value. The moment coefficient versus lift coefficient plot for three elevated settings at negative 15, 0, and 15 degrees show one of the lines, the pink one, which is for negative 15 degrees, to pass through the origin. The moment is 0 for that CL and elevator input. Therefore, for the best trim performance at the CG location of 35% of the mean aerodynamic chord, an elevator trim of negative 15 degrees works best. This moment coefficient plot versus lift coefficient for different CG positions represents longitudinal stability. A key indicator of a stable aircraft is if its plot is negative. A positive plot indicates an unstable aircraft. The black and green lines form negative 25 and negative 50% CG positions of the mean aerodynamic chord appear to be stable. The Albatross would be highly unstable at 100% of the mean aerodynamic chord as indicated by the dark blue plot. When the CG position is coincident with the neutral point, the static margin is 0, and therefore the plot would be completely horizontal. The light blue and yellow lines are close to this, which are for 25 and 50% CG of the mean aerodynamic chord. I would estimate the neutral point to therefore be around 40% of the mean aerodynamic chord. The combined nose gear steering and rudder input provides sufficient authority for maneuvering the aircraft on the ground. However, high-speed steering would increase the risk of the wing striking the ground and also put high lateral forces on the nose gear. This could cause nose gear failure. The minimum speed needed to achieve wheels off the ground is about 23 meters per second without flaps. With flaps, this is 21 meters per second. This is much greater than the predicted 10.5 meters per second stall speed. At 25 degrees trim and 22 RPM, cruise flight can be achieved at roughly 20 meters per second. With an elevator trim of 40 degrees, the minimum steady level flight speed was 17 meters per second. The maximum steady level flight speed was roughly 58 meters per second, requiring just negative 1.9 degrees elevator trim. Finally, after configuring the Albatross, we can validate and verify its systems by performing a flight test circuit around the checkered pylons on the airfield with a target altitude of 30 meters and a target cruise speed of 20 meters per second.